Hello, everyone. My name is Masoud Mansoury. I'm a PhD student at Eindhoven University of Technology. The paper that I'm going to present is FairMatch, a graph-based approach for improving aggregate diversity in recommender systems. Co-authors of this paper are Himan Abdollahpouri from University of Colorado Boulder, Mykola Pechenizkiy from Eindhoven University of Technology, Bamshad Mobasher from DePaul University, and Burke from University of Colorado Boulder. Generating fair recommendations in recommender system is the key element of success in e-commerce and social networks. Unfair recommendations will negatively affect the satisfaction of both suppliers and end users. There are various factors that lead to unfair recommendations. Popularity bias is one source of unfairness in recommender systems that causes low coverage of items in recommendation lists and unfair distribution of recommended items. So in this paper, we tackle unfair distribution of recommended items by improving recommendation diversity. There are two notions of recommendation diversity: individualist diversity, which is how diverse the list of recommendations is for each user, and aggregate diversity, which is how diverse the list of recommendations are for all users. But high individualist diversity does not imply high aggregate diversity. For example, assume that our recommendation algorithm recommended 5 different items to each user. So in this situation, we have high individualist diversity because each user received 5 different items as recommendations. But aggregate diversity is low because among many items that we have in the system, we only recommended 5 items to the users. There are some problems with low aggregate diversity. A recommendation system with low aggregate diversity only focuses on a limited number of popular items, which in long run, it might negatively affect users' experience in terms of item discovery. And also, it may cause an unfair distribution of items across recommendations from the supplier's perspective. So in this paper, we address this problem and aim at improving the aggregate diversity of recommender systems. Our idea in this paper is that we introduce FairMatch, a general graph-based algorithm that works as a post-processing approach for improving the aggregate diversity. The goal in FairMatch is to improve the visibility of high-quality items that have low visibility. For example, assume that we recommended 4 items to user U1, and these numbers are the visibility of each recommended item across the whole recommendation list. For example, the number 70 here means that item I2 is recommended to 70 users. And the goal is to generate recommendation list of size 2 for each user. As you can see in this example, item I3 has very low visibility, although this item can be another relevant item for U1 because the predicted score for this item is high. So in FairMatch, the goal is to find items like I3, which have low visibility, and promoting these items to be shown in the recommendation list of size n, or the final recommendation list for each user. This chart shows the process of FairMatch algorithm. Given a long recommendation list of size t, it creates a bipartite recommendation graph. Then it computes the weights for edges on the graph. And in the third step, it solves maximum flow problem to identify the high quality items that have low visibility. And in the last step, it constructs the final recommendation list of size n for each user. So in the first step, it is graph preparation, which we create a bipartite graph from the recommendation list, where the left nodes are the recommended items and right nodes are users, and edges are the recommendation between users and items. We also add 2 special nodes to the graph, source and sink nodes, as you can see in the graph here. And in the second step, which is weight computation, we use this equation, which is a weighted sum of item visibility and relevance, to compute the weight for edges between left and right nodes. So in this equation, Degree I is the visibility of item I. It is how often item I is recommended to different users, and rank IU is the relevance of item I for user U. Actually, it is the position of item I in the recommendation list of size T for user U. And alpha is a coefficient to control the trade-off between accuracy and diversity. So for edges connected to S1 and S2, we just simply and equally distribute the total capacity of left and right nodes to the edges connected to S1 and S2. For more detail on this computation, you can see the paper. And the third step is candidate selection, which we run we solve maximum flow problem on the graph that we prepared. For this purpose, we use one of the efficient algorithms for solving maximum flow problem named push relabel algorithm. Push relabel algorithm has two key operations, push and relabel. Push operations send a specific amount of flow to a neighbor, and relabel operations change the label of a node under a certain condition. But to better understand how this algorithm works, let's look at an example. So assume that this is our original graph, which two attributes, excess flow and label, is associated to each node, and each edge has weight and the flow that can be sent through this edge. And also, as part of this algorithm, it creates a residual graph that adds backward edge for any edge in the graph. And now assume that our current node is U, and we want to use excess flow to its neighbors, V and K. So one rule here is that if a node wants to send its excess flow to its neighbors, it must have higher label value than its neighbors. So here we see that label value for U is not greater than label value for V and K. So first we have to run relabel operation to increase the label value of U, and now we can send the flow to U's neighbors. So U sends flow of amount 8 to V and 4 to K, and then we update the excess flow of each node. But an important question here is how does the push relabel algorithm can find high quality items that have low visibility? To answer this question, I propose three claims. Push relabel starts with equal excess flow for all left nodes. As we explained in previous slides, we observed that FairMatch assigns equal weight for all edges connected to S1. Here is W. And also we initialize the label value for each node as follows. S1 has the highest label value, which is the total number of the node in the graph. And also we assign value 2 for the label of left nodes, value 1 for the label of right nodes, and 0 for S2. So before we start running a push relabel algorithm, we run a pre-flow process that sends the flow from S1 to the left nodes. So after running this pre-flow process, all left nodes will have excess flow of W. So now in the graph, we have at least one node with excess flow greater than 0, and it is ready for running push relabel algorithm. One important point here is that when we run push relabel algorithm, all left nodes must send their excess flow to their neighbors, to the right nodes. Okay, but if, for example, if a left node is connected to an edge with low weight value and cannot send all its excess flow to the right nodes, it has to send its remaining excess flow back to S1. So this is an important point. So in the left nodes, we will have some nodes that have to send back their remaining excess flow to S1, right? And in the second claim, we know that S1 has the highest label value. If we want to send back the excess flow of left nodes, send back the excess flow from left nodes to S1, we have to first run relabel operation. So by running relabel operation, those left nodes will receive the label value of this amount, which is 1 more than the label value of S1. For example, if I1 is one of those left nodes, the label value for I1 would be increased by this amount. And when push relabel algorithm terminates, the left nodes with label value greater than this amount, the total number of nodes in the graph, and also their connected right nodes would be returned as the high quality nodes that have low visibility. But why this happens, we can see the third claim, which is, let's look at this equation again. low degree here means low visibility. Because, for example, if a left node has low degree, it has low visibility because we said edges are the recommendations. And low rank means more relevant. So, for example, if an item is in the first rank of the sorted recommendation list, the first item is more relevant item. So, low visibility plus more relevant means low weight. So, items connected to edges with low weight are more relevant items that have low visibility. So, this is the answer to the above question. And in the last step, we need to mix the identified items with the recommendation. So with the top end recommendation generated by a standard recommendation algorithm. So for this purpose, we first sort the top end recommendation list generated by standard recommendation algorithm based on the visibility of the recommended items, and then we just remove the high visibility items from the list, and we add the identified items by FairMatch to the end of the list. And for experiments, we use two datasets, opinions and movie lens dataset, and also we use two base recommendation algorithms, one factorization model and neighborhood model, and also these are the other settings for our experiments. And also we use these baselines to compare the effectiveness of our FairMatch algorithm. And this table shows the performance of different rankers on opinions dataset for the initial recommendation list of size 50. For the whole results, you can see the paper. But here, we use 4 metrics to evaluate the effectiveness of each technique. Precision, coverage. Coverage is the ratio of the items in catalog that are shown in the recommendation list. And Gini index and entropy are the measures of fair distribution. So as you can see here, FairMatch has negligible loss in precision compared to other techniques and also the standard one. But it provides the highest and also significant aggregate diversity compared to other techniques. Its aggregate diversity is significantly higher than other techniques. And also in terms of generating fair distribution, for example, based on entropy, we see that FairMatch has the highest entropy value, but the improvement and difference is not significant. And also we perform analysis on long tail coverage, except on both datasets, except for user kernel on movie lens dataset, this plot here. On other cases, we see that FairMatch, the purple bar here, provides higher long tail coverage compared to other techniques. So in conclusion, we propose a graph-based approach, FairMatch, for improving the aggregate diversity of recommender systems. FairMatch re-ranks the output from the standard recommendation algorithm such that it improves the aggregate diversity of final recommendation list while it maintains the accuracy of recommendations. Our experimental results showed the superiority of the FairMatch algorithm compared to other state-of-the-art methods. Thank you for your attention.